In today's video, we're going to discuss an idea that is central to the definition of the fundamental group. This is called homotopy, or more explicitly, homotopy equivalence. So the first thing that we need to do is set down some notation for our fundamental group. For a path-connected topological space, let's call it X, we're going to denote the fundamental group by this symbol here. It's a pi with a lower 1 in the subscript, and then your space X goes in the brackets. This is an entire group. Remember, that means that it is a set endowed with an operation. It has identity, inverses, and all the good stuff that groups have. So, for example, we saw in our live session that the fundamental group, or pi1 of S1, is the integers, which we represent as Z. Okay? So here's a problem that you come across almost immediately when thinking about the fundamental group. It fails as an invariant, at least a topological invariant, to distinguish some pretty basic features. For example, the fundamental group is quite insensitive to dimension, which is a pretty obvious topological invariant. So to see this, I'm going to show you that the fundamental group of the circle is exactly the same as the fundamental group of the cylinder. The key observation here is that if I just have a loop on the surface, and the loop doesn't go around the circle of the cylinder, so it doesn't in particular go around this rod that goes right through the cylinder, then it can be shrunk down to a point, just like this. Okay, I can shrink the loop down to a point, and that is the same thing as the loop that does absolutely nothing, or the trivial loop, right? And in talking about the fundamental group, we often refer to this as the trivial element or the identity element because it does absolutely nothing. It functions as the identity of the fundamental group, right? On the other hand, it's more interesting to consider the case where your loops go around your cylinder. Maybe I'll do one that goes around twice. So I'll just do something like that. And then I'll make it meet back there. Okay. So actually, let's do it like this. Let's draw it starting from here, and then I'll make it cross over itself to meet back up there. Yeah. So now we got a loop that goes around twice, and so every loop that goes around the cylinder twice is going to somehow be deformable to a loop that looks like this. Again, the analogous thing on the circle is a loop that goes around the circle twice. Obviously, I can't draw it very well, so I'll have to draw it a little bit off the circle, but I want to imagine the green thing is completely lying inside the white line. Okay? So from this observation, it's pretty easy to see that the fundamental group of the circle, which is Z, is the same thing as the fundamental group of the cylinder, because using this loop that goes around the center of the cylinder, we can generate all the different types of loops you could get on the surface of a cylinder. So the fundamental group fails to distinguish dimension. Right? And obviously these two spaces are not homeomorphic because one of them is dimension 1 and this one has dimension 2. Okay? So here's our motivating question now. Does this mean we have to scrap all of our fundamental group work? And before we go ahead and just get rid of it, we have to consider that although it did fail us in these very simple tests, it did succeed in differentiating between certain tricky topological spaces. For example, you may remember that the Euler characteristic, right, it failed to distinguish the cylinder from the torus. It was not able to tell the difference between the two. It gave you the same number. However, the fundamental group is able to distinguish these two. So in that sense, it is better than Euler characteristic. So it seems like this fundamental group may be like another dummy invariant. It doesn't do the greatest job, but it is able to do a good enough job in some cases where other invariants will fail. So here's the fact that we're missing. It's that the fundamental group is not exactly a topological invariant. Of course, there's no such thing as a perfect topological invariant, but the fundamental group is actually more properly labeled a homotopy invariant. It is invariant under another relation, which we're going to discuss today, called homotopy equivalence. Right? So as you might be able to guess from our example with the circle and the cylinder, the circle is homotopy equivalent to the cylinder. And I'll discuss what that means intuitively. So homotopy equivalences include homeomorphisms, but they can also accommodate some nice dimension reduction. So to give an example of this, we're going to look at the example of bubble letters. Now, I want you to imagine that this bubble letter is like entirely filled in. Right? So we're allowed to shrink it within the confines of itself. And what I'm going to do is I'm going to shrink it first to the skeleton here, right? So a homotopy is often represented by these lines. What I can do is I can draw white lines that connect my outer shape, which is the white bubble letter, to the inner shape. Now, my bubble letter, remember, is completely filled in. So I'm transforming my filled in bubble letter to this skeleton green A. Okay? And the way I want you to interpret this is that the points on the white lines will get dragged towards the green, and you can sort of play it like a movie, right? So in the span of 1 second, every point on the white bubble letter is going to get shrunk down into the green skeleton letter, right? So points that are closer will get there first, and points that are farther will follow them closely behind. But essentially, once we're done this, we will end up with a skeleton A, right? And this is a homotopy equivalence. An easy way to think about it is a movie that allows you to do some continuous shrinking. Okay? So we can actually do another homotopy equivalence. And this time we're shrinking away these loose edges here, this and this. Right? So what I can do is I can imagine a movie where those edges, they follow along that white line until they reach this point here or this point here. And what will happen is that at the end of my movie, every point that is on a white branch is going to get shrunk into that point. So what I'm going to be left with is essentially a donut or a hole, just a circle. Now, you may be wondering, well, maybe we can take this even farther. Maybe we could shrink this whole thing to a point, right? We could just take every point on the green and draw these white lines to the center and then shrink them all down to a point. Well, this is where the homotopy is not able to do this. So the problem here is that if I drew these white lines, they are not inside the shape anymore. Remember, my shape is literally just this green loop here. There's nothing on the inside. So the thing about homotopy is that every sort of intermediate step has to be found inside the actual original shape. So this is not permissible. Right? So roughly speaking, a homotopy will allow for some dimension reduction. It can shrink away lines and whatever, but you cannot cancel holes and you cannot rip, tear, or glue, just like you could not do with homeomorphisms. So to illustrate the point further, I have a couple of examples. I have transformations on the right-hand side of one object to another, and I will tell you whether they are homotopy equivalences or not. Right? And in the case where they are, we say that the spaces are homotopy equivalent. Right? So the first one is the cylinder to the circle. An easy homotopy equivalence is found just by taking every point on the cylinder and smushing it down to this bottom circle. Right? So in particular, this circle right here is going to stay exactly where it is. And every point on these white lines is going to, through a movie, get shrunk down all the way to the bottom circle of that cylinder. So this is a homotopy equivalence. On the other hand, if I were to do this with a cylinder going to a torus, I would have to somehow glue together the bottom and the top. And this is not permissible. We're not allowed to glue in a homotopy equivalence. Now, like I mentioned before, you cannot take an empty circle and shrink it down to a point, right? That would require you to draw these lines going towards the center and reaching towards that center point. But these lines will no longer live inside my circle S1, so this also is not a homotopy equivalence. On the other hand, if I had a solid 2-ball, remember a 2-ball is just a disk in the two-dimensional plane, it's solid, so what I can do is I can take every point on the disk, and in a movie, I can shrink them all down to that center point there. So this one is a homotopy equivalence. This one's a little bit tricky, right? So study this example well and understand why the second one is a homotopy equivalence while the first one is not. They look similar, but they aren't. In a very similar way, we can do the same trick with the torus and the filled-in torus. So the solid torus, you may think, is homotopy equivalent to the circle, and namely this core circle that goes around the donut hole. Right? But this is not possible because if we just take a look at this cross-section here, if we were to drag points on the surface of the torus to that interior circle, right? The green circle that I had here before, just redraw it. Then I would have to somehow cancel out that hole, and moreover, these white lines don't even live on the torus. Remember, the torus is just the surface, it's not actually filled in. So this thing here is not a homotopy equivalence. However, if I were to fill in my donut and make it solid, like I've done here, then all of a sudden these lines, they do exist inside the solid torus. So this is a homotopy equivalence, where I shrink down every point into that core green circle. Similar thing is going to happen here for S2 and B3. So S2 is the two-sphere, it's just the surface of a three-dimensional ball. And this one cannot be shrunk down to a point via a homotopy equivalence. So let me just fill this in. And the reason why is because if I were to do that, it would force me to somehow cancel out that sort of hollow inside the sphere. You can see this more explicitly, of course, if you draw the lines that illustrate where points on the sphere would have to go. And notice that for all these lines, they never actually lie entirely inside the sphere. However, when you fill in the two-sphere to make a three-ball, so that's a three-dimensional ball in three-dimensional space, then all of a sudden this does work. So this is a homotopy equivalence. So now that we've discussed that, we're going to talk about one special type of homotopy equivalence, namely the homotopy of paths or loops. The way to think about this again is a homotopy, and what we're doing is we're taking one path and deforming it to another while fixing the endpoints. Right? So this here, as I've drawn, is a homotopy because I can drag points on the white along these extra, let me color them actually, I'm going to make them blue, along these blue lines. Okay, and of course I can't do all of them, but essentially if I follow along all these points, so let me actually go ahead and divide this into like maybe 3 sections. So it's 1, 2, 3. Now you may be a little confused of what's going on here, so I'm gonna explain that in a sec. Oops, that's not what I want to do. I want to get something like this. All right, so these new lines that I'm drawing right now, they represent important moments in time. So namely at the 1/3, 2/3, 1/4, 2/4, and 3/4 mark of our movie, right? So our homotopy, we're interpreting it as a movie that takes the white line to the green line, and these blue vertical-ish lines are just checkpoints. So this is going to be at the 1/4 mark, the 1/2 mark, and the 3/4 mark. Okay? And our white line is going to follow along these blue paths to their respective point on the green. Okay? So this is a really important idea because this is how we're going to define the fundamental group. Now, I'm not going to redefine everything today, but I'm just going to show you what we mean when two loops are the same in the fundamental group. Okay? And it will be a little bit more rigorous than what we discussed last time. So instead of just thinking about paths, we can think about loops. So I'm going to draw a more interesting space here, the torus, but before that, maybe I'll just draw a schematic of what's going to happen. So in the same way how we had paths being deformed to other paths, now we're going to take loops and deform them to other loops. Okay? And the idea is that if in my big topological space, I can deform them freely without running into any trouble, I can deform the white to the green, then we're going to say that the white loop is, in the fundamental group, the same thing as the green loop. Up to homotopy, it's no different. Right? Now, obviously, there's going to be an issue if there is a hole in the middle of my topological space. So for example, let's say I have a hole here, right? So now no element of my path can go around this hole or can go through this hole. So now if I try to do this white line thing, you'll notice I have an issue because how am I going to get around this hole, right? At some point, I'm going to have to like switch sides, and then there's not going to be a way for me to properly send the white loop to the green loop, okay? All right, so with that being said, let's go to my more complicated example. So again, in the fundamental group, we're going to use homotopy of loops to distinguish which loops are the same. And here I have two loops, the blue one and the green one, going around the surface of the torus. And what I want you to see is that these two are actually the same up to homotopy, which means that they can be shifted along the surface of the torus to turn one into the other. So to see this, I'm going to do the white line thing. I'm going to draw some lines, and you will be able to see that if the green loop follows these white lines, you'll be able to deform it into the blue loop. Okay? So now where it goes into the back side of the torus is going to be a little harder to see. So I'm going to draw these with dotted lines. And I'm not going to complete them, just so that the foreground is preserved. And this one is going to go right up here, just like that. Okay? So hopefully you see now how the green and the blue are related. I could sort of drag together the blue so that it becomes exactly where the green one is. And I can do this without doing any cuts, tears, or going out of my torus in any way. Okay, so I think that's a pretty cool illustration of what we're trying to do here. And of course, these types of loops would not be deformable to a loop that, for example, looks just like this on the surface. So if two loops in X are homotopic, that means that they are in the same class when we're talking about the fundamental group, and that means that one can be continuously deformed to another. Okay? So our intuition is, our illustration to show how important this idea is going to be by taking a space, looking at its fundamental group, and then considering what another space is just by removing one point and how that changes the fundamental group. So to illustrate, here I have again the unit disk, and we know that this is homotopy equivalent to a point. We can shrink everything down to a point. However, if I take a point out of my unit disk, let's say I remove this point right here, right? All of a sudden this is no longer homotopy equivalent to a point, because if I were to try to shrink everything down to a single point, maybe I don't even have to choose this red point here, I can choose another point. I can try and shrink everything down to this, but that's not going to work, right? Because eventually one of these points is going to have to go through the red or go around the red, and that's going to sort of cause a break in the circle, in the boundary. Right? So this is not an admissible homotopy equivalence. In fact, what I want you to try and figure out is why this is homotopy equivalent to just a straight circle, no interior filled. So this here is often called a punctured disk. Or if I make the hole a little bit bigger, like this, it is an annulus. Okay, so think about this one. And try and draw a diagram that sends the white, or the annulus rather, to this green interior circle. Okay? So our last definition is going to be really important for distinguishing a particular type of space and its fundamental group. If our space is path connected and it has a trivial fundamental group, then we say that our space is simply connected. Simple connectedness is very important. It is an idea that extends outside of algebraic topology. You hear a lot about it in multivariable calculus and complex analysis, and generally in manifold theory. So our interpretation of simple connectedness is that every loop can be shrunk down to a point. Why does this mean that my fundamental group is trivial? Well, it means that since every loop can be shrunk down to a point, every loop is in particular shrinkable to the loop that does absolutely nothing. And remember, that trivial loop is exactly our identity element. A group with only the identity element is the trivial group. Trivial because it only has one element, and it's basically the smallest type of group you could get. Right? So we say our space is simply connected, and our intuition is that if we can shrink every loop into a point without somehow leaving the space, then we're fine. We're simply connected. So I'll show you two examples and then leave you a couple others to do as exercises. Here I have R2, all of R2, and I'm going to take away one point. Okay? So this is not simply connected, and although you may think it is at first, because let's, for example, this loop here, it can be shrunk to a point, right? I'll shrink it to this point. Here's a white line diagram where I just take every point on my green loop and I shrink it down to the white. Okay? However, you can probably see why this fails when I take a loop that goes around the red dot. Okay, and this is because at some point we're going to have to sort of skirt around the red in order to reach our final point. And at that point, right here, there's going to be we're going to force a break in the loop if we're going to actually squeeze it through. Right. So there are multiple ways of thinking about this, and lots of fancy illustrations you can do in your head to try and understand this better. Try and come up with something that works. I'm just presenting my own personal way of viewing these things. Okay? So on the other hand, if I were to take out a little, let's maybe take out a loop. So let's take out a loop here. Right? Now all of a sudden, this one, it is in a sense simply connected, and in another sense it isn't. It is not simply connected because by our definition, now we have R2 minus this red loop. I'll just draw it like this. And it's not simply connected because it's not even path connected. Remember, in simply connected, we require our space to be path connected. However, every loop can be shrunk to a point. So for example, if I take a loop in here or a loop in here, right, those ones can be shrunk to a point. But actually, this loop over here cannot. Right? So here I've made a pretty big alteration to my space. I've taken out this entire curve here, and because of that, I've ruined simple connectedness. Right? Okay. However, in this path component, the one on the inside, right, this little thing here is simply connected. Right? It's just the outer part that you can't shrink every loop down to a point. Okay, so hopefully those two examples provide you some intuition on how to tackle these problems. I'll now present the rest of the 4, and then we'll be done. So in this example, we have R3, and we're going to do the same thing. We're going to remove a point. Okay, so of course, a loop that lives somewhere out here can obviously be shrunk down to a point. That's not very difficult. But the problem is, what if I have a loop that goes around like that? Or maybe I'll illustrate it a little bit better, going behind and around, like that. Okay? So think about that one. Another one is where I remove an entire axis. So let me remove this entire axis. Of course, the problem is now not when the loop is out here, but rather when the loop somehow goes around this here, and it can go around a number of times, right? So here's one that coils around a couple times, 3 times actually. Let me just fix up this picture a little bit. So think about this and whether this space is now simply connected or has trivial fundamental group. Our last 2 examples also involve R3, except this time instead of removing a point, I'm going to remove an entire unclosed curve. Now, I want my curve to have endpoints, so I can really say that this thing is bounded, right? And again, the issue is going to be when our curve maybe goes around this red thing here. So is there a way to shrink this green curve to a point without touching the red? And lastly, here's our last example where I'm going to take excuse me, all of R3, but I'm going to take away this red loop here, right? So it's going to be sort of similar to what I did here, but there's an extra dimension. So not only now do you have to think about loops that are in here or out there, but you also have to think about loops that go around. Just like that. Okay. Fix up this drawing here. All right. Okay, so have a think about these 4 examples, and I'll be able to give you solutions in about a week's time.